Okay, third video of the gases unit is looking at Charles's law. So Charles's law is going to be able to relate gases and temperatures for us. So first lesson, we talked about all the different properties of gases. One of the properties we talked about was that as the temperatures increase, the volume of the gas is also going to increase, right? We talked about taking a balloon, blowing up inside your house, and then putting it outside where the temperature was much colder, and seeing that the volume of that balloon really shrunk down. So what we find is that unlike Boyle's law, where they were inversely proportional to each other, when it comes to volume and temperature, these are directly proportional to each other. So as one goes up, the other goes down. So we find that we can say that V is directly proportional to T. Okay, so one goes up, the other goes up. One goes down, the other one goes down. Okay, so this relationship is linear. So that means when we start looking at generating the equation, we don't have to worry about like putting inverses and things like that in. The only thing though that we do have to worry about is temperature. Okay, and that's because if we use degree C, which is what we generally use, we get 0 as a temperature. And we don't want that, because if we actually put 0 into a calculation, we would get 0 as the answer. And you should know, hopefully, that at a temperature of 0, volumes of gases are not 0, right? You don't walk outside and suddenly have no volume on a day where it's 0. So what you find is that we actually use the Kelvin scale, okay? And we call that the absolute temperature scale. Okay, we represent it with capital K is the symbol for this. So what we find is we have what's known as absolute 0. Okay, so absolute 0 is the temperature at which theoretically a gas is going to occupy 0 volume. Okay, last I heard we haven't actually quite reached this temperature yet, but we've definitely gotten super close to this temperature. So absolute 0 is at negative 273.15 degrees C. Okay, so for that reason, we have this little converting factor down here. We did talk about this when we looked at gas stoich in the stoichiometry unit. Okay, so what we find is that T, and that capital T is our Kelvin temperature, is equal to our lowercase t, which is our degree C temperature, plus 273.15. So what you will find on the equation sheet is that you will see that it says 273.15 Kelvin is equal to 0 degrees C. So you would have to be able to recognize that if you were converting a degree C into a Kelvin, you would add them together. And if you were taking a Kelvin and trying to get a degree C, you would actually be subtracting that 273.15 from it, okay? Some questions will give you the temperature in Kelvin, some will give it to you in degree C. It's really important in this unit that you never use degree C, okay? And the reason for that is you're going to see when we get to generating our equation, the equation we generate isn't valid for degree C. It's only valid for Kelvin, okay? So never use degree C in a calculation, only Kelvin, okay? So let's look at how we are going to generate that equation. So Charles's law is where this is going to come from. So I said on the previous slide that when we look at volume and temperature, there is a linear relationship. Okay, but what you find is that this is only true, well, not only true, but we're going to generate ours to be in Kelvin, okay? It's still linear in degree C, but you'll see, and I'll sketch you the graph in a second, that it definitely looks different. So when we do volume and temperature in Kelvin, we get a straight line that goes through 0. Okay, why you have to use Kelvin? So let's say instead I graphed out, sorry, that's kind of crooked, volume, but then over here I did temperature in terms of degrees. No, that's not what I want to do, hold on, degree C. So what I would find here is this would be 0 degrees C. That's not where the volume of my gas equals 0. So this would actually extend this way. And what I would find is that the curve or the line would look more like that, right? And so I don't want this when I'm generating an equation. And the reason I don't want this is, remember yesterday, or I guess potentially not yesterday, potentially today if you're watching the videos on the same day, but in the last lesson, we talked about being able to get rid of B because we said the intercept was 0. So that's true for Kelvin, but it's not true for degrees C, right? I do have an intercept, okay? That is why the equation we're going to generate is only valid for Kelvin, because it would be a totally different equation for degrees C because there is a B value here, right? Because this is here, there is a B, okay? So not using this, we're going to use this one over here, okay? So going to do the same thing as we did in the last lesson, right? We have y equals mx plus b. So we replace y with v, right? Because that's what we have over there. M can stay. X is the temperature in terms of Kelvin. And we can get rid of b because the intercept is 0. So again, if we want to rearrange this like we did yesterday, and we want to isolate the m, right, I would have to divide by t to be able to do that. So we get that v over t is going to be equal to m. Okay, same thing as the last lesson as well. If we take two different points on the line, so we take this one and we take this one, and we say this is point 1 and this is point 2, we can relate v1 t1 and v2 t2 because the slope of the line never changes. And that's why we can generate the equation of v1 over t1 is equal to, sorry, my computer's being a little slow and I'm typing it, it's not actually typing till a second later, is equal to v2 over t2. Okay, so in here, unit-wise, volume can either be milliliters or liters, as long as they are the same. Temperature, though, must be Kelvin. No option on it, has to be Kelvin. So if the question is giving you degrees C, you're going to have to convert it to get it into Kelvin. Okay, you can't just be like, oh, this is degrees C and this is degrees C, I can plug that in. You can't, because this equation was generated for a temperature in Kelvin graph, not a temperature in degrees C. Okay, so this basically gives us Charles's law. I'm not sure why my thing plastered over that. I don't think I can move that. Probably not. Oh, I can look at that. Okay, so we get that Charles's law states that the volume of a fixed amount of gas, right? So you find we're always saying a fixed amount, and that's because if you change the number of molecules, you are going to change the volume of that gas. So we're always assuming it's the same amount, either in moles, molecules, whichever unit you want to use, that is there. Constant pressure, because like you learned in the last video, if we change the pressure, we are going to change the volume. And when we're looking at Charles's law, we only want to consider temperature as a variable, okay? So it is directly proportional to the absolute Kelvin temperature of the gas. So there's our equation of V1 over T1 equals V2 over T2. Again, this equation would be provided to you. You don't have to memorize it. But important thing is, again, being able to sub things in, recognize you need Kelvin. Biggest issue you guys tend to have with this equation is solving for temperature. You guys don't have a big issue solving for volume because you're like, oh, I need to solve for volume, I'm just going to move the temperature over here. Your issue tends to be when you're solving for temperature. That some of you are like, oh, I need to isolate temperature, I'm just going to move the V1 over here. But then what you don't recognize is that you've actually solved for 1 over T1. And that's not what you're looking for, right? We're not looking for the inverse of T1. We're actually looking for T1. So if I was trying to solve for T1, right, I would have to move that up here, which means the V2 would have to move down here, right? So I would swap them. And then because I would then have T1 over T2, I would have to move this T2 over here, okay? So temperature does definitely get a little bit messier, right? So if I was solving for that T1, right, that rearranged equation, once we did all that manipulating I just talked about, would be the V1 times T2 over V1, right? Because the T1 moved up here to where the V2 was. The V1 stayed, but the T2 moved up here, and this V2 and getting it away from there moved down here. So it does take a little bit of practice. Again, those of you that are really math inclined will be like, I don't know what you're talking about, Miss Chip. That's the easiest thing I've ever done. But some of you definitely do struggle with solving for temperature. And this is where you really want to check at the end, does my answer make sense? So you would look at what happened to the volume. If I increase the volume, I'm expecting the temperature to have gone up. If I decrease the volume, I'm expecting the temperature to have gone down. And if I don't have that, then I probably haven't rearranged my equation properly, okay? Yeah, so let's look at an example. So a balloon inflated with air in a room at 24 degrees C has a volume of 500 mils. The balloon is put in the freezer at 0. What is the new volume? So we have our V1 as 500 mils. I can convert it to liters if I want, but I can leave it in milliliters. I just have to recognize that that means my V2 that I calculate is also going to be in terms of milliliters. Okay, so T1, it's at 24 degrees C. We said we can't use degrees C, right? We have to use Kelvin. So I have to do the 273.15 plus the 24. Okay, watch your sig digs when you do these, because remember we're doing addition. So we're looking at decimal places. So 2 numbers after the decimal, 2 numbers after the decimal. So even if I was going to have to round for significant digits, I wouldn't do that until the end. So this gives me 297.15 Kelvin. Okay, all of these numbers are significant because 2 numbers after the decimal, 2 numbers after the decimal, here's 2 numbers after the decimal. So I have 5 total numbers. Sorry, someone has like a super loud car or something. Okay, so here's my V1 at 500 mils. Here's my T1 of 297. Okay, my T2 was actually pretty easy to get because the temperature was 0. And 0 plus 273.15 is just 273.15 Kelvin, right? So notice I converted both of these degrees C into Kelvin. You have to do that. No choice. I can't just be like, oh, but they're the same. I'm going to plug them in. Remember we said the equation we generate is only valid for Kelvin. Okay, so what are we looking for? We are looking for V2. So we have our starting equation, which is V1 over T1. And that was equal to V2. Where's my typing going? Over T2. Sorry, someone has a very large, obnoxious truck. I think it's jacked up about, I don't know, 3 feet above the tires. I'm sure you can hear it. Okay, so V1 over T1 equals V2 over T2. We are trying to solve for V2, right? So this is what we want to isolate. So we need to move that T2 over here, right? This needs to go up there so we can isolate that V2. Okay, once we do that, we come up with V2 equals V1 T1, no, not T1, sorry, T2, and that does definitely tend to be a common mistake. We want to put the 1s together and the 2s together. You have to be careful when you are in the this unit that you don't always do that, right? Sometimes we do and sometimes we don't. Just really depends on how that equation needs to be rearranged, and that would be over T1. Okay, so there's our equation. V2 equals V1 T2 over T1. So You have to be careful twice with this. You have to be careful in rearranging that you put the T1 and the T2 in the right spot. You also have to be careful in subbing in that you actually put T2 in here and T1 down here. A lot of times you guys just kind of go like right across. You're like, oh, here's the V, here's the T, here's the other T. Be really careful when you are doing the temperature ones in particular, because they're the ones that tend to be a little messed up. So we are going to have V1, which is 500 mils, times T2, which is 273.15 Kelvin. And we are dividing by 297.15 Kelvin. So if we think about this, even before we get an answer, we decrease the temperature, right? We went from 24 to 0. If we decrease the temperature, we should expect that the volume gets smaller. If I get an answer that isn't smaller than 500, one of two things has happened. I've misrearranged or I've misplugged in my numbers, and I should figure out which one and fix it. Okay, so 500 times 273.15 divided by 297.15, I get, how many significant digits? 3, so 460 milliliters. This is smaller than what I started with, which is what I expect. Because my temperature decreased, my volume was supposed to decrease, okay? So always do that quick little check to make sure that it has worked. It takes 2 seconds to do it, and it's a really quick way to double check that you've rearranged properly and substituted properly, because honestly in this unit that tends to be the biggest issue you guys have with calculations, is just like plugging things in improperly or rearranging incorrectly. Okay, so now we have to bring it back to the kinetic molecular theory, okay? So when we talked about it, we said that the Kelvin temperature is directly proportional to the volume. Okay, the other thing we find is that temperature is technically a measure of the kinetic energy of molecules. And if you remember back to last year when we talked about kinetic energy, we said that EK equals 1/2 mv squared, right? So we're not changing the mass of the molecules, but what we are changing, right? So just writing that equation out, you don't ever actually have to use it in Chem 20, but just kind of reminding you of it, right? So the mass of our molecules isn't changing, but the velocity can. So the more kinetic energy my molecules have, the more velocity they have. The less kinetic energy they have, the less velocity they have. So what that basically means is that at higher temperatures, gases move faster. Okay, they have a higher velocity. And at lower temperatures, gases move slower. So why does this matter? Well, remember we talked about pressure is equal to force over area. So although in temperature, I've changed the temperature, I haven't changed the pressure. But if we again think about our lovely little balloon as our container, we still have an internal force equaling an external force. But what we find is that if we increase the temperature, the molecules inside of here start moving faster, right? So think about if you get in a car accident going at 10 kilometers an hour versus 100 kilometers an hour. It's going to hurt a lot more when you hit something going at 100 kilometers an hour because there's a lot more force involved. So what we find here is the same is kind of true for gas molecules, although they don't have feelings, at least I don't think they do. But what we're going to find is that as the temperature increases, the force of the collision is going to be significantly higher, which means the internal pressure is going to increase. But we haven't changed the external pressure. Now we have an imbalance, right? The internal pressure is higher than the external pressure. So our container is going to either have to expand or contract until we get those pressures equaling each other. Okay, so because at higher temperatures, they are moving faster, we can say that this means there's more force to the collision. Okay, this increases the internal pressure. So now we have that pressure imbalance. So how are we going to fix the pressure imbalance? Well, we can't change how much force they're hitting with because that would involve changing the temperature. We're not changing the temperature again. But what we can change is the volume of the container. So if we start to expand the container, they're now going to hit less frequently. So although they're hitting with more force, they're not hitting as frequently, which overall is going to drop the total amount of force, which is going to bring the pressure down. Okay, this is why we find we need a larger volume to decrease the number of collisions. Okay, so at higher temperatures, because our gas molecules are moving faster, they're hitting with more force, we need a larger volume so that that internal pressure is equal to the external pressure. Okay, the opposite is true at lower temperatures. Okay, we find that at lower temperatures, our gases move slower. So if they're moving slower, that's going to mean there's less force. And if there's less force in every collision, there's less pressure. So now again, we have a pressure imbalance between the outside not having changed and the inside having decreased. So how we're going to increase the pressure, again, we can't change how fast they're moving because that's dependent on temperature. But what we can change is how often they're going to hit the sides of the container. So we need them to hit the sides of the container more often. The only way to make them hit the sides of the container more often is to have a smaller volume to increase the number of collisions. Okay, so half of this unit has to do with the math part, and half of this unit has to do with the theory part. So some of you really like gases. Some of you find you're like, you know what, I'm really good at the calculations, but the theory really stumps me. You do definitely want to make sure that you have a pretty good grasp of both, because generally it's kind of an even distribution between theory questions and math questions that we're going to ask you, because the theory is important and the math is also important. So the majority of the explaining of the theory really comes down to how many collisions, how strong are the collisions, right? More collisions, stronger collisions, more force. Less collisions, less speed, we find less force, which means less pressure, okay? So that's basically your Charles law. It's relating temperature and volume. We find that they are going to be directly related. Next laws that we are going to look at in the next video are going to look at how we kind of bring all of this together.